I'm Leo. I'm part of LI.F I, and today I'm going to be talking about a new thing we've been working on for the past 8 months or so. The title of the talk is Stop Writing Routers. I'm a dev, and I'm very concerned with dev UX. It's a topic that is very close to my heart. And what I've been working on is kind of a new mechanism to redo some of the plumbing that we have had for a long time now to make it easier to expand horizontally to new protocols. As I said, I'm Leo. I'm the head of research and development at LI.F I. I started as a backend dev, worked a bit on the smart contract side, so I kind of touched most of the code base, let's say, and I have a good overview to start thinking about possible improvements. At LI.F I, we aggregate things. We aggregate things very widely. There's a lot of aggregations. We support more than 60 chains, more than 20 dexes, more than 20 bridges. We have over 100 smart contracts. This is a huge surface for issues, bugs, and it's really hard to maintain them. What we're trying to look at in this talk is gonna help with specifically this problem here. Nobody wants to maintain this amount of smart contracts. It's a big issue on the security side, but it's also a big issue because every time you add a new smart contract, you need to have auditing concerns, and it takes a long time also from the engineering point of view. So yeah, we're gonna focus on this. Specifically, we want to focus on what composability means. Everyone talks about the DeFi Legos in the space, and composability is always kind of a core concern of a lot of projects, but not very often the technical details of composabilities are discussed. In this slide, I try to make it very visual, kind of simple, a bit mathsy, but not too much, to try and understand what we mean with composability, what's possible, what's not possible, what the ideal case is, and what the real case is. So here on the right, you see some base operations. You can think of these like kind of core primitives of the protocol. I listed 3 of them. For example, a swap from token A to token B via UniV4, a bridge via a cross, or a deposit of a token into a morphovault. You can imagine these as things that we code. They're not really mutable. They stay on chain and then they live there. On top of these base operations, we create flows. So we have these composite, I'm going to move on the other side. We have these composite operations that use the base operations to perform some meaningful action. Maybe not a good spot. In this case, I showcase a swap and bridge flow and a deposit and bridge flow, trying to use kind of a mathsy function composition language. This is what the concept should look like for composability, and if it was like this in reality, that would be perfect. But that's never the case. It's never that simple. There's always edge cases, always things we need to change that are specific to some flow or some tool. And in this case, it's still oversimplified, but the idea is that for a swap and bridge, there are concerns that are kind of invisible in this view, right? For example, whenever you do a swap, you want to stay within slippage, so you need slippage checks there. If you're bridging native, a lot of bridges require you to wrap it first. Or maybe you are handling a specific partner flow that requires 2% fees on USDC only. And these are not super strange or extremely wild conditions. We have seen this happen a lot of the times. This landscape often turns into this landscape, which is, we named it death by 1,000 adapters. You end up having so many smart contracts whose sole purpose is to adapt to other contracts. And we started off with, this and that. That was probably the first 2 smart contracts we wrote 4 years ago. And then we started slowly increasing the surface, right? Maybe we want to bridge with some extra checks, or we want to swap without fee collection because a partner doesn't want to have fee collection. Or this is a funny one, you want to zap into a vault, but the vault requires native, so you need to wrap it first. All of these conditions, as I said, lead to sprawling smart contracts. We do not want that. That's bad. Why is it bad? Is because of this and this. Writing contracts and auditing them is very expensive, both time-wise and money-wise, because auditors are very well paid, way more than me. So yeah, and the moment requirements change after an audit, you got a problem because you got to go back and write a new contract, and nobody likes to do that. And the kind of pattern that arises with all this is that we are an aggregator, and most of the code that we run on chain is not really business logic. It's what we call glue. You could also call it plumbing. It's really just the plumbings, the tubes that move information between very well established contracts. Like, you have a cross, you have Uniswap, and then those are immutable. You don't really touch them. They're outside of our product domain. But in order to move funds between them and then compose complex flows, you need this plumbing. And that's what aggregators do, or at least that's kind of what we do most of the time. Just to get, this is the most technical I'm gonna get, but I wrote a very, very simple pseudocode bit. It's not super visible, at least not to the naked eye, but this swap, deposit token, and bridge text is LI.F pink. The idea is that the pink things are external business logic and the white things are glue. So this is a swap and bridge flow. We are looking at an instruction for depositing some token A. We get the amount of the token in some variable deposit amount, and then we calculate how much fee we're going to take, and then use the amount minus the fee to swap, and then whatever the swap gives out, we want to bridge. So again, this is what we call glue. I wanted to make this slide just to make it clear of what I'm referring to. Any question up till here? No, doing good. Okay, and I guess the question that we had like about 8 months ago was, is there a better way of doing this? Like, why do we need to hard code this glue on chain when the glue in reality doesn't really matter? Like, as long as you enforce the right checks and you use trusted protocols like these ones, glue should be kind of malleable. We should be able to change it without the whole rewrite, audit, deploy cycle. So can we somehow inject this glue? So glue becomes a parameter. The scenario would look something like this. Again, pink is trusted base operation on chain, and then white is glue. I mean, in this case, I guess there's a white component that should have a different color, but whatever. The point is, you have some contract on chain that we can call flow executor for all intents and purposes, that takes some flow specification. So what kind of operations you want to do in terms of these base actions. And then once you put this flow specification into the flow executor, you get some new blockchain state. This is the desired outcome, right? And the kind of question that comes to mind, if you accept that we want to try and go this direction, is what kind of minimal operations do we need? Like, we've seen that if we go back to here, we had a lot of these base operations, and they're very specific, right? Like this operation, for example, is specific for UniV4. You will have one or more per protocol usually. So the moment you want to try and simplify things on chain, you need to ask yourself this, like, what are the minimum operations that we need? And after a bit of thinking, God damn it, the spacing. After a bit of thinking, we kind of found out that there are 3 main operations we care about. First one is store and read intermediate results. So you should be able to do something on chain and read the side effect of that thing. And then do the opposite, right? You want to do something and store the side effect of that thing somehow. The other one is encoding a contract call. So in order to call a contract, I'm not going to go in super detail, but the point is you need to encode calls to contracts. And to do this, you need ABI and you need an ABI encoder. Having an ABI encoder on chain that is actually dynamic is not very easy, but it's possible. So that's the second action we want. And the third action we want is pretty straightforward. You encode the call, you also want to be able to use the call, right? You want to call things on chain. Turns out that this pattern that I'm describing is not novel. It's not a crazy new idea we came up at LI.F I, but what's my slide? Right. But it has a very well-known in NCS, very well-known name NCS, computer science. So landscape before is we got a lot of contracts on chain that go through the diamond router. This is like heavy on chain stuff. And then off chain, very little happens, right? I mean, you have the routing that Kenny described earlier, but in the end, what goes on chain from off chain is just minimal declarative information like swap info or like what bridge to use plus a few parameters. We want to switch kind of the paradigm on its head to go to something that looks like this. On chain, we have a flow executor. Off chain, we have the specification of the flow. What's the name of this thing in CS? It's a virtual machine. For those that are not computer scientists, maybe like you've heard virtual machine in the context of EVM or Solana. Conceptually, it's all the same thing. If you're not familiar with them either, you could think of a virtual machine as a processor, like a CPU. It's just a thing that knows nothing about the business domain you're working on, and then you just inject some kind of instructions onto it. It then executes those instructions, but it's not really tied to your business domain. It's just a flow executor. That's what I called you earlier. This, I'm not going to go into detail, is the diagram for the architecture of the VM I'm specifically talking about. You can like take a screenshot or like stop the video if you're watching from home and look at it. But it's just a fetch the code execute cycle for a VM, nothing too crazy. There are a few benefits that are very clear of this architecture. You can script flows of chain. So in the same way you have like scripting languages like Python for doing like simple operations on data, for example. With this new architecture, you will be able to do tiny scripts that then get executed on chain. And the cool thing is you don't really need to do them in Solidity. You can do them in a high-level language that is designed for Web 2 computation, like TypeScript. Integration happens in Web 2 land. What does this mean? It means that whenever we're horizontally scaling, so like adding new protocols to the core offering that we have, those integrations don't happen in Solidity anymore. So the moment we want to support, say, an ERC for 626 volt, like Morpho, we don't need to create a smart contract for Morpho and audit it and then deploy it. And then when Morpho releases, Blue version 2, change it. We just have a tiny TypeScript adapter that then encodes this flow logic. And then that can be used through the pipeline that we constructed and then sent to the virtual machine on chain for execution. This is my favorite point through composability. It's always like, oh yeah, we have money Legos. Now, do you really like this kind of design? Not this design specifically, because like we haven't created the best virtual machine out there, but like this kind of design really does bring true composability onto the table. Like it makes it possible for complex flows to be scripted from top to end outside of the blockchain. And really, yeah, that gives you true composability. An interesting one is also gives the caller control of execution. The caller that actually sends the transaction on chain knows everything that is going to happen up to the base operations that we discussed, right? So it doesn't know maybe what's happening inside of a cross, but they should be able to know what funds are going into a cross and what funds are going out of a cross. Touching on the security side, we have less contracts. So we went from a landscape of like 100 plus contracts to like, I think it's 8, 7? It's a few contracts. So it should mean like, more security, right? Because we have a smaller surface area for bugs. In reality, it's not more secure, but you're moving security up the stack. So security now lies in how you integrate these protocols in TypeScript land and how you simulate the execution before sending the call to the user, and how you enforce certain semantics that you want to remain invariant, let's say. This could be like static checks, like you're never sending to the address 0, or like you're never calling a contract that is not being deployed, such stuff like that. So yeah, security landscape is slightly different and it's half the stack, but it's still there. Something that is crucial for this to work properly and not get hacked is that the virtual machine needs to be sound. Sound is intended in a kind of a Matzy way, like sound as in it needs to be specified correctly, and then the actual implementation needs to abide 100% to the specification. Specifically, you need to be sure that there's no memory corruption possible. That's because you don't want people to get control flow access. Like control flow must not be hijackable. This is kind of a hard one. You need to have correct dynamic ABI encoding. Solidity does not support this at the moment, so we had to create bespoke contracts to do dynamic ABI encoding. This is crucial for the preparing cool data for the contracts you want to call. And then this is also an important one, like you want to have proper reentrancy approvals, proper reentrancy and approval semantics, as in you want to make sure that approvals are gated correctly. You don't want people to have access to a generic executor that shares approvals with other people. And then, that also the reentrancy concern, but that's more or less true for all smart contracts. In order to get all of this right, we ran 3 audits. One of them was with a partner, Recon, that I wanted to give a shout out to, because it really allowed us to nail down some things that are not really easy to express and check. So Recon, they do invariant-based auditing, or like you could call it invariant-based formal verification or fuzzing. They provide strong guarantees that you just don't get with manual audits. 3 key properties that they allowed us to kind of verify and like be more confident about is that you basically model the expected system behavior of your thing, and then the invariant checking kind of does the heavy lifting of saying, hey, these invariants that you defined are actually holding for most cases that you could ever encounter, or all of them, depending on if you can actually do formal verification or not. It depends on the complexity of the algorithm. Also, you can define doomsday states. A doomsday state is a state you'd never want to be in. And then Recon is able to, read your doomsday states and give you very big red flags if they ever happen. They should never happen. Never. And then you also get much stronger regression guarantees. So the idea is that with Recon, we were able to create a suite of known edge cases, known flows we want to support, and then say that we improve the virtual machine and add the new operations to it. Those regression tests, which in this case are invariant checking tests, they still exist, and they allow us to check whether they are still valid or not. So, it's a very powerful tool. We had great collaboration with them. Yeah, Recon, check it out. Cool. We're almost at the end. We achieved so much with this. I call the Aggregation Unchained, because really with this much composability, you can do a lot of things that we weren't able to do before. Earlier, we were bound to ERC20 interactions only. This unchains us from this thing. Like we can now use ERC721, ERC4626. Really, anything that lives on chain can be targetable through this VM architecture. An interesting one is positive slippage capture. Because we are able to dynamically prepare call data for invocations, on-chain invocations, the positive slippage can be accounted for. So whenever you do a flow like a swap and then a zap, you can always capture every positive slippage that came out of the swap and then put that into the zapping step that you are performing afterwards. It's non-trivial to do with RVM. If you think about it, you will realize that's true. And then this architecture allows us to have clear, faster integration velocity. Like clearly writing TypeScript, it's faster than writing Solidity, and also like it's more powerful. You can do async stuff too. You have much more control over event emission. So if you want bespoke partners to have particular event emission patterns, you can have it without breaking anything on chain. And you can also do routing beyond one-to-one flows. So you can do one-to-many or many-to-one or many-to-many. It just really depends on what your glue looks like when you inject it in the VM. I didn't touch on this. The point, like the TLDR of that is transaction generation becomes really fast, like extremely fast. Just the transaction generation side of our pipeline is below 1 millisecond. The routing is a bit more, but the best kind of the average case for a transaction to this new system is about 100 milliseconds. If you are in cluster, is 50 milliseconds. So it's still very fast. For the next steps, I mean, there's a lot of next steps. I think we have, what, 80 Jira issues? No, GitHub issues, not Jira, for the upcoming month or so. But these are the three main points that are kind of interesting for people looking at this from a customer point of view. Adaptive quoting, that's very interesting in my opinion. Right now, the jumper and like LI.FI API kind of is mainly concerned with price sensitivity, but not all users are like price sensitive. Like maybe they are speed sensitive. So we want to make the routing adaptive in that you provide the parameters according to what you want to achieve with it. And then the routing figures out, okay, these are the things I need to do to maintain the best response speed or the most accurate quotes based on the current liquidity. Currently, this system is intended for zaps. We wanted to release it quickly, so zap support is what is available in V0. But through the LI.FI core routing, this is integrated as a DEX pretty much. So you also get swapping and bridging out of the box. It's just not handled by this system. Later on, we want to move all of the DEX and bridge aggregation into the system to make it more of a cohesive and then single responsibility service. Not in a bad dev way, in a good dev way. And then the most important one, I think, is third-party self-integrations. At the moment, we are dealing with integrations ourselves, as in we are writing the TypeScript required for the plumbing. We want this to be outsourced, as in people should be able to self-integrate. There are still a couple open threads on how to do this safely and what exact direction we want to take. So I can't exactly give you a ETA for this, but the best I can say is soon TM. Yeah. Composer is live. You can try it. It's a jumper.exchange. Basically, any flow that requires you zapping into a vault or out of a vault should be handled automatically by Composer. This is available same chain and also cross chain. Yeah. Example of same chain flow. In this case is USDC to staked INA. You can see that there's a swap between USDC and INA and then a Composer step between INA and SINA. And yeah, that's it. Thanks for listening.